So students, in this lecture we will be discussing a very important concept. As I have already told you, it will be about derivations of formulae in limit state method. But before deriving the formula of in LSM, derivation of formula in LSM, I would like to tell you that when we were discussing about the working stress method, when I did the derivations, what I did, I took a singly reinforced beam, right? You remember that I took a singly reinforced beam and then I did all the derivations. But in this case, the derivations of formula in LSM, I will be telling you about the basics. Okay, I will not be taking a concept of singly reinforced beam and deriving all the formulae. That we will be discussing in detail when I will be teaching you about the design of beams, right? So in this chapter, we will be discussing about the derivations, or you can say that the basics of derivations of formula in LSM, right? How the derivations are done in LSM. So what is the basic concept? Okay. So first of all, before starting, let us see the stress strain curve for concrete. This is stress, this is strain curve for concrete. I told you that in the ultimate load method also, the basic assumption was that the maximum strain in concrete is 0.0035, right? In ultimate load it was 0.003 or 3%, right? But in case of limit state method it is 0.0035 or 0.35%, right? And the strain up to which the concrete shows elastic behavior, it is actually 0.002. Now why I have drawn it parabolic? Because in actually this limit state and ultimate load method, we take the non-linear relationship between stress and strain. On the other hand, in the working stress method, what we are assuming, we are just taking the linear relationship between the stress and strain, which is also known as the idealized graph, right? I told you about it, right? So up to 0.002 strain, it shows a, you can say, elastic behavior. If you remove the forces, it will tend to come back to its original position. But after this, permanent yielding will happen in the structure. Okay. So and 0.0035 strain is the maximum strain which a concrete can sustain. After that, it will fail, right? It will collapse. So the maximum strain in concrete is taken as 0.002. The maximum strain in concrete is taken as 0.0035. Clear? Now, this is for steel. The stress strain curve for steel. The stress strain curve for steel. I have already explained you these things, right? Now, in the case of concrete, it is 0.67 FCK. How 0.67 came? Due to size and shape effects, right? And I divided by 1.5 because I told you that the basic advantage or the main advantage of limit state method is that it has two partial factors of safety. First of all, with load, and second with the strength. So here, if I divide the strength, the characteristic strength with partial factor of safety 1.5 for concrete, I get the characteristic strength is 0.446 FCK. For this, I have to design the structure. Clear? Now, similarly for steel, this is Fy. What is Fy? The yielding strength. What is yielding? At which there is a, you can say, gradual increase in the you can say the size of the reinforcement. Okay, steel, size of the steel. Because I told you that for mild steel you have a permanent, you can say, curve. This is lower yield point, upper yield point. So we say that lower yield point is the yielding point. But in case of your high strength deformed bars, high yield strength deformed bars, what we do is that we take a line parallel to the initial stress strain curve at a strain of 0.002, and the line where it meets, we get the yielding point, right? So the code says that the maximum strain in concrete at collapse. It means that when the steel will fail, the maximum strain in steel, not concrete, in steel, it is actually 0.002 plus 0.87 Fy divided by Es. Now how this has come? I told you that stress is directly proportional to strain, right? But in case of steel, the stress is taken as Fy divided by the partial factor of safety 1.15. It should be equal to Young's modulus of elasticity of steel into strain of steel. Clear? Now if I am taking the yielding, because if I take the yielding, I am taking yielding. If I am taking the elastic, I will take some elastic stress. But I am taking the yielding stress at which there will be a permanent deformation in steel, right? If I divide it, you will get 0.87 Fy divided with Es, and you will get the strain, or you can say the plastic strain. So the elastic strain, which is 0.002, corresponding to the elastic strain of concrete plus this value. How much is this value? That is 0.87 Fy divided by ES, right? So the code also says that the maximum strain in steel at failure is given by 0.002 plus 0.87 Fy divided by ES. And what is the value of ES? If in question it is given to you, very good. If it is not given to you, you have to remember that for structural steel, the Young's modulus of elasticity, it is taken as 2 into 10 raised to power 5 Newton per atom square. Clear? Now, this is the basis of design. Now, let me explain you about the ultimate neutral axis, or you can say the critical neutral axis in case of a singly reinforced beam. This topic we will also be discussing in detail when I will be teaching you about the design concepts. But why I have put this derivations of formulae in LSM? We could also do this topic in design of beams also, but because some basic questions have been asked from this topic in GATE. So that is why I have put a separate topic of derivations of formulae in LSM. Otherwise, we will also be doing derivation of formulae for singly reinforced beam, double reinforced beam. But why I have put this different topic? Because a lot of questions have been asked from these graphs actually. Right? So let us see what are the questions and what are the concept and how we derive it. So first of all, let me explain you about the ultimate neutral axis, or you can say that the critical neutral axis in case of a singly reinforced beam. After that, we'll be proceeding further. So let us see the graph. So I'm rubbing it. Now, till the time I rub this and I start the topic, just recognize and recall that when you have to get the critical neutral axis in case of LSM, it is known as the ultimate neutral axis, XU, right? XU max. But you have to, if you have to calculate the critical neutral axis, what you had to compare? You had to compare the strain diagram. I explained you that, right? You have to compare the strain diagram, right? And when we are getting the, we were deriving the, in the case of working stress method, when we were deriving, we were getting the value of the normal neutral axis. What we used to do? We used to compare the static equilibrium, C is equals to T. Remember that, right? So that concept will be used here also, right? So let me draw the strain diagram. So the strain diagram, let us say this is a beam, singly reinforced beam. Just for the time being, this thing will be discussing in detail in design of beams also. So the strain diagram will be something like this. Let us say this is the ultimate neutral axis, XU, or the critical neutral axis in XU. Ultimate neutral axis, right? This is steel, this is concrete. The strain in concrete, the strain in steel. So up to what limit does the concrete shows a linear behavior, or you can say elastic behavior? It is actually 0.002. 0.002. And what is the maximum strain in concrete as per the code? That is 0.0035. I told you that, right? 0.0035. Clear? Now, what is the maximum strain in steel as per the code? That is 0.002 plus 0.87 Fy upon ES. So this value will be equal to 0.002 plus 0.87 Fy divided by ES from here to here. Clear? Now, if this is XU and let us say this is D, small d, effective depth, then this value from here to here, okay, so I have drawn it up to here, so it will not be up to here, it will be up to the center of the reinforcement. I have already explained this thing, right? Center of this reinforcement, 0.002 plus 0.87 Fy divided by ES, right? And this value, this distance, it will be equal to D minus XU. Simple, right? Now this is the basics, right? Basics of determination of ultimate neutral axis or the critical neutral axis. Now let me do the similarity of triangles. Now from the similarity of triangles, this angle is equal to this angle, this is 90 degree, right? This angle ultimately will be equal to this angle. So from AAA, angle property, what I have, these two triangles are similar. So for in these two triangles, if I do it like this, that 0.0035, or let me take it like this, that XU, or let me take this triangle, D minus XU divided by XU. D minus XU divided by XU is equals to 0.002 plus 0.87 Fy divided by Es and divided by 0.0035. Simple, just by the similarity of triangles. Now what I have to do is that I have to reshuffle it. Let me divide this d divided by xu minus 1 is equals to 0.002 plus 0.87 Fy divided by Es and divided by 0.0035. Simple, right? Now what I have to do is let me take 1 there. If I take 1 there, what it will become? It will become plus 1. Clear? It will become plus 1. Let me again reshuffle it. I will get d divided by xu is equals to 0.002 plus 0.87 Fy divided by Es. If I take the numerator as 0.0035, it will be added here. 0.0035 divided by 0.0035. If I again reshuffle it, if I add these two values, it will be equal to 0.0055. So let me write it here. So d divided by xu, it will be equal to 0.0055 plus 0.87 Fy divided by Es and divided by 0.0035. Clear? So dear students, this question has been asked many times even in GATE examination as well as other lot of examinations. So this is very important, right? So the question is like this: which of the following equations is correct, right? So option number A, some value will be given. Option number 2, option number 3, option number 4. Among the 4 options, one option will be this. So a lot of students get confused that from where this has come. So a lot of students I have seen that usually this option is also given in question. That is 0.002 plus 0.87 Fy upon Es divided by 0.0035. So I have seen a lot of students taking this option because they are familiar with 0.002. Yes, I know 0.002. In equation it was 0.035 also, but they forget that if you there is a minus 1 also. If you add it, you will be getting 0.0055. So I have seen a lot of students doing this silly mistake, right? And this question has been asked many times, and many numericals have also been asked based on this formula. You are given the value of the effective depth. Es will not be given to you. If it is given, well and good. If it is not given, it is 2 into 10 to the power 5. I already told you, right? Fy, for different type of steels, Fy has different values, right? And similarly, you will be getting different values, right, of xu limiting. Clear? Okay. So that is how you solve these types of numericals. So this was my main motive, to add another topic named as the derivations of formula in LSM. Otherwise, I could solve this thing in design of beams also, but that will be a you can say not parallel things, right? So the parallel thing would be, first of all, do the basics of derivations of formula in LSM. That this is the basic, right? After that, we'll be driving the singly reinforced beam when we are designing the singly reinforced beam, right? So this is very important. The question is, sir, do I have to remember this formula because it is very tricky, right? 0.0055 here, it was 0.002. It depends on you whether you want to learn it or not. Okay, my advice would be, if you learn it, well and good. If you can't learn it, just understand the graph. It will take just hardly 10 seconds to drive this, you can say, the similar triangle property, right? Because if you ask to me, I have not learned this. I don't remember it actually, right? When I was driving it, then I came on this conclusion. Actually, I don't remember the formula, right? I just remember the similar triangle property. Clear? So this was the basic, right? Now, if you put the different values of Fy and say different values of Es, you will be getting different values of Xu. Now, what are the values of Xu? Now, let me rub this thing. Let me rub this thing and write it directly. Now, this is also important, right? So, if you put E is equals to 2 into 10 raised to the power 5 and Fy is equals to 250. Fy 250 for mile steel, right? So you will be getting Xu is equals to 0.53D, number 1, right? If you are putting, if E is equals to again the same 2 into 10 raised to power 5 and Fy is equals to 415, not 415, yeah, take it 415. Then you will be getting Xu is equals to 0.48 D. And if this is equation number 2, and if the E is same, E is 2 into 10 raised to power 5 and Fy is 550, you will be getting Xu is equals to 0.46 D3. All these three equations, again I am repeating, all these three equations, equation number 1, equation number 2 and equation number 3 are very important, because many times many numericals, many theoretical questions, especially numericals in this portion, have been asked in GATE examinations, in ESE examination, in state level examinations, right? But the GATE people, they are mainly focusing on this topic. Why? They will not, nowadays they are not asking direct questions actually. Now what are they doing is that, I told you that it is a straight line, the strain curve. Sometimes they can say that let it be a straight line up to here, and from here to here it is a rectangle. Clear? This they can also say, or they can say that let the elastic strain, it is not 0.02, that it is 0.0015, and that it is not 0.035, that it will be 0.029, something like that. Then what will the value of Xu? So if you have just mugged up the formula, if you have just memorized the formula, it will not take you anywhere. So you must know that with the similarity of triangles, these equations have been derived. I have seen a lot of questions, right, like this. For example, it was 0.002. In some numerical, it is given 0.0015. Or take it at 0.0029. What will you do then? If you apply this formula, your answer will be wrong. Simple. Right? So you have to see how this formula has been derived. Otherwise, in GATE examination, if you study very deeply, there are a lot of derivations. You will be confused. It will not be possible to even finish the syllabus. Right? Okay. So what we have to do is that only main derivations or main formulae derivations have to be learned. Right? So this is very important. Otherwise, I could also write directly the formula. But the thing is that you should know how it has been derived actually. Clear? Now let's meet at the next video and solve a few numericals based on this topic, which have first of all I will be solving some numericals which I feel that can be asked, and I will be giving you some numericals. Let us solve a few numericals and it will further strengthen your concepts. So let's meet at the next video.